Okay, here comes problem 20. Let's read this problem together. It's a pretty long one. A standing desk has 31 height settings numbered from the lowest one to the highest 31. So, okay, 31 different numbers to be achieved. And since the desk is not working properly, when the up button is pressed, the desk goes up 6 settings at a time if possible. So if you go up, you have to go up by 6. And if you choose to go down, then you have to go down by 4. So you cannot move by 1, and this is the this is the hard part. And then if the desk starts at setting number 1, how many of the 31 is attainable? How many of them can be reached? For example, if you want 1, and you can choose to go up by 6, not by 1. You must go up by 6. Then you are going to 7, right? And you can choose to go down by 4, and you can go to 3, and so on. It's a going up by 6, going down by 4, and blah, blah, blah. So you will see that actually the final result would look like, it look like this. We don't need a problem anymore. This is the problem, okay? And this one would look like 1 plus 6x minus 4y, okay? You're gonna move up by x times and then move down by 4 times, and then you have this number. That means that this is an even number. This is an odd number. Because this is even, this is even, and 1 is odd. So in total, it has to be an odd number. So 2 is not achievable, nor is 4, nor is a 30. Anything between 1 and 31, but it has to be an odd number. That's it. And let's just double check to see if it is true that every number is achievable. Say we need 1, 3, 5, right? All the way to 29 and then 31. So how do we go from 1 to 3? It is super easy. You just go up 6 and go down by 4. Go up by 6 and go down by 4. That is equivalent to going up by 2. So you can always go up by 2 by keep doing this, right? And from 3 to 5, you go up by 6 again and then go down by 4 again. Then you're at 5. So you can always do plus 2, right? You can always do plus 2. But keep in mind, for example, let's say we are already at 29. And let's see what we can do. Can we still go by 2? No, actually not. Not at least using this method. Because if you choose to go up by 6, then you should be at 35. But 35 is not a valid number, right? It explodes. There's a kind of a top. There's a top cover. There's a cap. The cap is 31. You cannot go over 31. So when you are at 29, actually you cannot use this method anymore. But what if I still would like to go up? Say if I am at 27, I can't do this because 27 plus 6 is already over 31 as well. And what if I'm at 25? This time is okay. So I keep using this method and I reach 25 and then I do plus 6 for the one last time and I reach 31. So far so good. So at least, and any odd number between 1 and 25, both ends inclusive, are achievable. We've already proved that. We can just keep doing this. Plus 6 minus 4, plus 6 minus 4. And then we're at 25. And once we are at 25, we can go to 31 directly by just adding 6, right? By adding 6. Then we are at 31. But we cannot go to 27 using the same method, right? Can we? Yes, we can actually. One last time, we minus 4, we go down by 4 and we are at 27. But once we are at 27, we cannot do plus 6 once more. So seems that 27 is okay, 31 by far is okay, but how about 20, how about 29? How do we achieve 29? We cannot achieve 29 from 27. As I said, 27 plus 6 would explode. But keep in mind, 29 is achievable from 23. And 23 is achievable. We've already proved that, right? It is under 25. It can be achieved from 21 by keep doing this. So 23 is achievable, and 23 plus 6 would be 29. So that proves that 29 is also achievable. Although this is the hardest number, but anyways, it's achievable. It's attainable from 23. So this proves that anything from 1 to 31, as long as it is an odd number, is achievable. 1 to 25, or all the way to 27, you can do this. Keep doing plus 6 and minus 4. You are at 27. And if you are at 25, you can just do plus 6 and then you are at 31. And when you are at 23, you can just do plus 6 and you are at 29. So every odd number within the range are achievable. So in total, how many odd numbers are there? That is last term minus the first term divided by common difference plus 1. That is 16 of them. We've got 16 odd numbers between 1 and 31. That is choice B. Okay, so this problem is solved. Okay, here we are at problem 23. Let's see. Okay, it's now in a camera. A rectangular prism, which is also a cube, has integer edge lengths and has a volume of V. The 6 faces of the cube are painted, a cuboid, technically speaking. And the cuboid are painted, and then it is cut into 1 by 1 by 1 cubes. Of these cubes, 50 of them are not painted. And what is the mean of all possible values of V? Okay, so see, let's say this is the cuboid. It is cut somehow. Okay, and then everything on the surface are painted. Everything inside are not painted. Everything inside is safe. Okay, and we've got a total number of 50 inside the cuboid. So they are the 50 of them are not painted. That is to say, if the size, let the size be x, y, and z. Let the size be x, y, and z. Of course, x, y, z is a 50 because it's the volume. And how about 50? That is x minus 2, right? What is contained inside is x minus 2 times y minus 2 times z minus 2. That is 50. This is a v. I'm sorry about that. Okay, this is where we can start with, and since we are looking for the average of all possible v's, so order actually doesn't matter here. For example, if we use a 3, 3, and 52, that is 1, 150. In that case, it goes to a v. And what if we use 350 and 3? That might be a different cuboid, but that goes to the same v. In that case, this v should be counted once only. That means that orders doesn't matter. So we assume that x, y, z are arranged in a, let's say, non-descending order. So it is going up or at least equal. This would be better so we can avoid making any repetition. Okay, see 50. So to get 50, we've got different possibilities. In terms of the brackets, we've got 1, 150. We've got 2. Okay, let's 1, 2, 25. We've got any more? We've got 1, 5, and 10. Okay, I think that's the end of the one group. And then let's do 2. 2, 5, 5. That's it. That's everything. Okay, that is in terms of the 3 brackets. So in terms of x, y, z, that would be 3, 3, and 52. Okay, this would be 3, 4, and 27. This would be 3, 7, and 12. This would be 4, 7, and 7. Okay, so in total 4 of them. And let's check if there's any repetition, coincidence. So this one has got a 13. No 13, no 13, no 13. Okay, unique. This one has got 3 and 3 threes, 4 threes. Not 4 threes, not 4, just a 2. Okay, no 3. Okay, unique. This one has got 2 7s. None of them has got 2 7s. Unique. And this one has to be unique as well. Okay, so there's no repetition. Let's just do some calculation. And finally, we have to divide everything by 4. So we want to keep things as easy as we can. This is 3, 3, 52. 9 times 52 plus 4 times 3 times, okay, 4 times 81 plus 12 times 21 plus the last one, 4 times 49. The whole thing is divided by 4. And that would be 9 times 13 plus This is 81. This is 3 times 21, that's 62, 63. This is a 4, so this is 49. And what's this number? 7, 117. Switch the order so we can make 10. Looks better. 180 plus, this is a 130. 310. Do you have that option? Okay, 310, here we go. So the answer is B. Okay, have a look again. We've got four different possibilities. Each one is ascending. Okay, we keep them non-descending, at least non-descending. So, and just to make sure that there is no repetition, and then we find the average of 4 possible V's. And V is calculated as X, Y, Z. So every number has to go up by 2. Okay, this is 1 is like x minus 2, so x is 3, and in that case we find x, y, z, and finally we have got 4 v's, and yeah, we end up with this number. And why I did this is that I want to keep the calculation as simple as we can, but there's nothing important in this part. Okay, that's it for problem 23. So let's move on to the next problem, which is problem 24. Problem 24, let's see, a 3-digit number is an integer from, okay, of course that is. And 3-digit integer is called tiny if no rearrangements of digits gives a 3-digit integer that is smaller. For example, 1, 38, 2, 7, 5, 6 is a tiny, but the other 3 are not. Okay, let's just check the 3 tiny ones. 138 is tiny, that is because if you rearrange it, for example, 318, this is bigger, so this number is the smallest possible arrangement. That is why this is considered as tiny. Now how about 207? 0 cannot go to the front, so you cannot mention this. This is not a valid number. It doesn't count. And among all valid arrangements, this is the smallest possible. So this is tiny as well. And here we've got 566. This one is tiny because you can swap them. But it doesn't consider, it's not considered as another arrangement. It's just the same. So among all possible arrangements, this is already the smallest arrangement. So this is tiny as well. Okay, that's the basic idea of tiny. And let's see how many 3-digit integers are tiny. Okay, let's see how many of them are tiny. So let's consider different cases. First of all, there's non-zero. Okay, non-zero cases. And later we consider 0 cases. Okay, the numbers which include 0 digit. And say there's no 0. And how many different formats do we have here? We have like ABC, that means all 3 numbers are different. Or maybe we have ABB and we have AAB, right? And that's it. Oh, or maybe AAA. Yeah, that's all of them. And see how many tiny numbers are of the format ABC. We pick anything. We pick 3 out of 9. And for any choice, we've got just one arrangement that is the smallest. So in that case, that is 9 times 7 times 9, it is 8, 7, 3, 1, 2. That would be, okay, that is 84. Okay, this is the everything for ABC. And how about ABB? If we pick 2 numbers as A and B, and we will end up with the only possible ABB or only possible AAB. So these 2 numbers, these 2 values are the same. Let's pick 2 out of 9. 2 out of 9. This and say if we pick 1 and 2, it has to be 1, 2, 2 or 1, 1, 2, right? So in ABB case, that would be that would be 9 out of 2. Okay, that is 36 of them. And here we've got another 36. Okay, so that's it. And please keep in mind, there's no ABA. Okay, by the way, ABA is not okay. ABA is equivalent to AAA because if B is bigger than A, then B is bigger than the next A, and this is not tiny anymore. So this one shouldn't be counted. That's what I'm talking about. That's why we've got only ABB and AAB, these two formats, and each of them would give a 36. And how about AA? Of course, it's just a 9 of them. So that's everything for non-zero part. And now let's move on to the zero part. There should be a zero, so it could be the smallest possible. It could be A0. Let's consider this case. Okay, A0B. It's just 1 0. And is it possible to have AB0? It is actually not possible because AB0, if you have AB0, why not A0B? Here, A and B are non-zero, okay, non-zero digits. So there's just 1 0. And A0B should be strictly smaller than AB0 for sure. That is why this format doesn't work. It has to be A0B. And A has to be smaller than B, strictly smaller than B, okay? And that would be the only possible arrangement for A0B. So you pick 2 out of 9, 2 as A and B, okay? You pick 2 out of 9, there's an A0B, and that is another 36, okay? And how about A0A or AA0? Is that possible to have A0A or AA0? Let's consider A0A or AA0. Which one is a smaller? Of course, this is one is smaller. And is this tiny? Yes, it is tiny. So this is also valid. This is not okay. This is 1 out of 9. That's 9 of them. Okay. Now let's consider 2-0 case. Is that possible that we have a 2-0 case and that is tiny? Yes, it is, because once we've got 2 zeros. This is the only valid arrangement, and of course that is tiny. So it is 9 out of 1. Oh, sorry, 1 out of 9. That is 9. So that is everything. Of course, we can't have 3 zeros. This is 1 0 1 0 with repetition. That's a 2-0 case, and that's everything. So how many non-zero cases do we have here? 84 plus 72 plus 9. And how many zero cases do we have here? That is 18 and 36. 18 and 36. Okay. 120. 99. 219. Do you have this option? 219. Okay, we've got this one. So the answer is E. Okay. 219 different tiny 3-digit integers. We consider 2 parts, and in each part, we've got different formats. Just be careful. Some formats like this, or like this, these are not tiny for sure, so we have to discard them. Okay, and consider the rest. Finally, you add them up, and you end up with the right number. Okay, that is all for problem 24, and now we are at the very last problem.